Okay, folks, you're very welcome. My name is Gary Gorman, and I am here to do today's session on the Leaving Cert Computer Science. So, you're all very welcome. I'll go through what we're going to do for the day first. I have some files shared with you on the YouTube link that you got, it's a Google Drive folder that the files that you're going to need throughout the day. If you don't have access to them, don't worry about it. I've got today's PowerPoint is in that in those slides, so that or is in that folder, so that you can access them and you can use them. There's way more in this PowerPoint than we're going to get through today. So there's we've only got about 3.5 hours, 4 hours. So there's loads more in there for you to help you with your revision for the Leaving Cert. Okay, who am I? I'm a PhD student here at ATU. I'm also a lecturer, and I'm a former Leaving Cert Computer Science teacher. So, how's today going to work? So the first thing we're going to look at today is we're going to look at search and sort. So this has come up last year, in last year's Leaving Cert in particular. Then after lunch, we're going to look at question C, the Python question in your exam. We're just going to have a look at last year's Python exam. We'll look at a few different solutions for the questions, and we'll have a wee chat about what's really expected from your Python exam. And then in the afternoon, we've left maybe the a wee bit less challenging stuff, the computational thinking. We're just going to be doing computational thinking. I don't think we're going to have time today to look at representing data. All right, the computational thinking question in your Leaving Cert. Okay, so search and sort, we'll have a look at that first. Representing data. Okay, search and sort. So there are several search and sort algorithms that you need to be familiar with for your Leaving Cert. So what is an algorithm to start with? An algorithm is a set of rules for getting a specific output from a specific input. So what does that mean? It's basically a list of instructions to get something done. All right, that's what an algorithm is. Each step must be so precisely defined that it can be translated into a computer language and executed by a machine. So basically we have an input, a process, and an output. What an algorithm is basically a strict set of instructions to perform a task. All right? So basically what we're going to look at today is we're going to look at some sorting algorithms. Don't think we're going to have time to get onto search, but we'll look at this. We'll look at a few sorting algorithms. So what is a sorting algorithm? It's basically an algorithm that puts items into order. All right? We're going to be looking at lists of integers, a list of integers, so that the list can be put into order. All right? So, to start with, the foundation of all of these sort algorithms is the swap algorithm. The swap algorithm can be if you don't understand the swap algorithm, it can be difficult to move on and have a look at the other sorting algorithms. The swap algorithm, we'll have a look at the code for this in a wee second. So here I've laid out some. This is a bit of Python code here now. And what I've got is I've initialized a variable Ronaldo7, Messi10, and what I want to do is I want to swap the value that's assigned to Ronaldo to Messi, and I want to swap the value that's assigned to Messi to Ronaldo. So I've tried to do it here this way, and I've intentionally done it incorrectly. Can anybody see a problem?
Because on the line before you said Ronaldo equals Messi, then when you're bringing it down, Messi equals Ronaldo. So Ronaldo's value has been overwritten.
Ronaldo's value has been overwritten. So the output here, whatever Messi is equal to 10. So now Messi and Ronaldo are equal to 10. The value that's assigned to both of these is now 10. So we can't swap them. We've now lost the value that was assigned to Ronaldo. So we have a wee swap algorithm, and I'll show you that now. Swap. Okay. So here we have, can you see that? Is that big enough? Yeah. Okay. So what we have here now is we have the code done incorrectly, and I just and I've highlighted here, the problem is both Messi and Ronaldo are now 10 is assigned to both of them. So that's a problem. So if I run that now, the output says Ronaldo's number is 10 and Messi's number is 10. So that we didn't swap them. So there's a few different ways that we can solve this problem. First of all, I want to comment that out because we know that's wrong. And here we have solution number 1. So I'll run this anyway first for the crack, and we'll show that it works now. So now what we want to do is we want to swap Ronaldo to 10 and Messi to 7. And you can see down here in the output that Ronaldo is now 10 and Messi is now 7. So we know it works. So what's happening? So the first thing we've done here now is we have created a temporary variable. And all it does is store the value of Ronaldo's number. All right? Do you remember in the previous example here, we overwrit Ronaldo here in the first line. So that was the problem. So we lost the value that was assigned to Ronaldo. So what we do is we create a temporary variable. And we store the value that was assigned to Ronaldo first. And then we get the value that's assigned to Messi, which is 10. We assign that to Ronaldo. And then we want the value that's assigned to Messi to be the value that was originally assigned to Ronaldo. So very simply, we've kept that value here under temp, and we assign temp to Messi. All right. So that's how that works. So when I was first learning this it took me a while for me to wrap my head around what was actually going on there, because you might have to grapple with that a wee bit before the penny drops. How's that sit with you? Do we understand it? It's quite. There's a bit going on there. Okay. So Python have come up with a cleaner way of doing it. And I'll show you that. A cleaner way of doing it that's more straightforward and easier to read. Okay, so this is the more Pythonic way of doing it. So basically what we can do is we can swap the values that are assigned to two variables this way. So we've got Ronaldo and Messi is equal to Messi Ronaldo. Simple. But what's going on under the hood here is exactly the same as this. It's the same thing. What's going on here, these are the exact same algorithm, do the exact same thing. It's just up here, we have to assign our own temporary variable, and a temporary variable is done for us here. So this will also work. So if we run that, and there we go. Ronaldo's number is now 10, Messi's number is now 7. Okay. So all of these files are shared with you. All the Python files that I've created for today are all shared with you in the folder that has been sent out to you. Okay, so they're all available to you, including the PowerPoint. Okay. Sort. Okay, so the first sorting algorithm that we're going to look at is called simple sort. Simple sort. This came up in last year's exam. It came up. They called it selection sort. So you'll see if you Google this, you'll see simple sort and selection sort. The same names applied to both of them. In my PowerPoint, I've referred to the first version of it as simple sort and the second version of it as selection sort. All right. So if you see it in different books done different ways, I understand. I've seen it myself. Okay. So simple sorting algorithm. So basically, what do we want to do with this sorting algorithm? We've got some cards here now, and we want to arrange them in ascending order. So we want to arrange them in ascending order. So we've got 4, 5, 6, 7, 8, 9, 10 in the bottom. So with the simple sort, it gets its name because it's the simplest sorting algorithm. It's the simplest one to understand. So basically what we do, we have our cards, and basically what we do is we scan over the cards and find the smallest card in the deck. And we take that card and we put it into a new list. All right? Then we scan the cards again, get the next smallest card, take that out of the original list and pop it into the new list. Okay, the process then continues until all the cards are sorted. Okay, and once all items have been removed from the unsorted list, the sorted list is then sorted. The sorted list is then sorted. Okay, so here is the pseudocode. Do we know? Have we heard the term pseudocode before? Pseudocode. Okay, what pseudocode is basically it's basically the algorithm written in plain English. The sequence of steps are as follows. So first of all, you initialize the unsorted list. So the unsorted list is your deck of cards to start with. All right, unsorted. You initialize an empty list. So we need a second list for this sorting algorithm to work. And this is where this algorithm begins to fall apart. So we repeat the following steps until the unsorted list is empty. So the first thing is we find the smallest item. And the second thing is we move the smallest item to the sorted list. And once the unsorted list is empty, we stop. Okay, I'll give you a wee demonstration in that just here we are. Okay. So here we have, I'm just going to take 5 of these cards, and we're going to sort them. Okay, so the first thing that we do is, very simply, we scan over the list, we scan over our unsorted list to find the smallest item in the list. We grab the smallest item in the list, and we pop it into a new list at the start of the new list. Then you scan over all the items of the list, and you find the next smallest item. You remove the next smallest item, and you pop it into the other list. Then we do the same again. This time it's 52. 52 gets popped into the other list. Then it's 60. And then we take 77 and we pop that in there. So that's simple sort. That's the simple sort. Can anybody see a problem with it? Has anybody come across these sorting algorithms before? No, that's good. This is new to everybody. So this isn't actually a revision. Okay. Let's put it a different way. Let's say we want to perform this task on something with very little memory, like a watch, or let's go with a watch. And it has very little memory, but the list has 1 million items. Anybody see a problem now? We have to make 2 variables. We have to make 2 lists. Exactly. So we've got 2 lists. So the problem with this algorithm is we need 2 lists. We need double the memory. We need double the memory, which is a problem. And there is a solution to this, and we'll look at that. We'll look at that in a minute. So we'll have a quick look at the code for simple sort. Now, I've shown this to students before. I've shown this, gone through these algorithms with students before, and it can be quite frightening. As far as the Leaving Cert questions so far, they haven't really gone into the code. So I'm showing you this as a demonstration. Don't be worrying if you find it very confusing and you get a wee bit lost. Chances it hasn't come up the code hasn't come up in the Leaving Cert before. If it did come up, I would imagine they would give you the code and ask you to recognize the code rather than you wouldn't have to write it. I don't think you would. Don't think you would have to write it. So don't get overwhelmed. Don't be thinking that you're going to have to memorize this. I don't think you will. Okay. So what's going on here? What's going on here? So we've got our unsorted list, and we have our sorted empty list. So our empty list is our sorted list is currently empty, and we're using a for loop here now. The for loop for I in range length of unsorted list, and then what we're doing is we've got a variable here called smallest, and the smallest. So have you ever seen this method here before? Min. The min method. So what the min method does, the min method will scan your list and find the smallest item in it and return that. Okay? And then what we do is we put this, we've assigned the smallest item in the list to the variable smallest, and then we're just popping that item into sorted list. And we've also got to remove it from the original list. Okay, so let's run that just to demonstrate, and you can see there now that the list is now sorted. So we'll have a wee scan. We'll have a wee scan over this now to show you exactly what's going on. Okay, so we have our unsorted list. We have our sorted list. We have our for loop, so we'll go into our for loop. So we're going to run this. We're going to run this for loop. We're going to run this for loop the amount of times that there are items in the list. So the length of the unsorted list is that 7? Well, it's going to be 7. We're going to run it 7 times, and then. So the smallest item in the list is currently 4. So 4 gets assigned to the variable smallest, and then 4 gets put into the sorted list. 4 gets popped into the sorted list, and you can see over here I've got my variables displayed here now, and 4 has just got popped into our sorted list. Very importantly now, I have the next line. The next line is really important, and this came up in last year's Leaving Cert. The unsorted list dot remove smallest. This is really important. So what happens now is 4 now gets removed. So you can see there now 4 is gone from our unsorted list. And then the loop starts again. And we go through the same cycle over and over again. So, I can't, off the top of my head now, from last year's exam, they asked, what is the significance of line 10? They didn't ask it like that, they asked it. What they did in the exam, I'll show you the exam paper in a wee while. They asked, why is it important, what is the significance of removing the smallest item from the original list? Why must we remove it? Any ideas? Exactly, exactly. If we don't remove the 4, you can see here now the 4 is removed on our first pass. The 4 is removed on our first pass. If we don't remove it, in our second pass, 4 will be the smallest item, and what we'll end up with is a list with nothing but 4s. It'll just be 4s. So that's critical. That's critical. That's critical, and that was asked in last year's Leaving Cert. Just so it's important that you can wrap your head around that. Okay, how's that, folks? Happy enough? Okay. So the main problem with this algorithm, as we talked about it before, is the fact that it has 2 lists, and if we have a million items in our list, then we need 2 lists that can hold a million items, which is a problem. Okay, so let's have a look. How do we sort this problem? So there's our algorithm. Simple sort. A note on performance. Simple sort is not an efficient algorithm. This is just, I'm just explaining what I've just explained to you. It requires twice as much memory as the size of the original list. So if you have a list with a million items, then you need 2 lists with a million items. To sort a list of size n, the algorithm needs a space requirement of 2n. So n, you're going to see this now over the remainder of this session. What n stands for is the number of items in the list. Okay? To sort a list of size n, the algorithm needs a space requirement of 2n. So we need if the list has a million items, then we need space for 2 million items. This is impractical with large lists, but there's a way around it. There's a way around it. And we call this selection sort. Selection sort. So selection sort solves this problem by sorting a list in place, so there's no need for a second list. Okay? And this also came up in last year's Leaving Cert. Here we have a list with a marker pointing at the first item in the list. So here we have now, we've got a marker pointing here, and we're looking at the first item in the list. So we find the smallest item to the right of the marker. So you can see here we've got our marker here now. And we swap this item with the item at the marker. So what do? Instead of us having a second list and reaching for the 4 and putting it into our second list, instead of that, what we do is we have our marker here, and what the marker is doing is identifying the one card that we're going to compare with the smallest card to the right of it. Are you with me? So here's 9. 9 now, so what we do is we scan all the cards to the right of 9, and 4 is the smallest card to the right of 9, and we do a check. Is 4 smaller than 9? If 4 is smaller than 9, we swap them. Here's our swap algorithm. All right? Then what we do is we increment our marker. What does increment mean? Anybody? Increment? Just move forward by 1. Okay. So we increment our marker. So this is now our second pass. So we're now, the marker is now pointing at this card here, number 6. 6 is compared to the smallest item to the right of it. That's 5. And then we have our if statement. If 5 is smaller than 6, swap them. So here, there we go. Now 5 5 has been swapped with 6. Then we increment our marker. The same thing happens again. We scan all the items to the right. We scan all the items to the right, and we find the smallest item. The smallest item in this case is 6. If 6 is smaller than 10, swap them. Where are we now? If 6 is smaller than 10, we swap them. We were here, that's right. So now we increment the marker to here. We scan all the items to the right. What's the smallest item? The smallest item is 7. So when the smallest item is 7, we do our if statement again. If 7 is smaller than 9, we swap them. You got me? So that there continues all the way as we go down. That continues all the way as we go down. All right. So I'll give you a demonstration of that on our wee website there that I showed you a wee minute ago. Okay, so here we have it. I'm going to new cards. So I'm going to just going to do 5. Okay, so I'm going to pop my marker here. All right, I'm going to pop my marker here. So what I do is I scan all the items to the right of the marker and I find the smallest item. If the smallest item is smaller than the marker, then we swap them. So you notice this is all happening in place and we don't have a second list. So now we move the marker over to the right. Now that's the problem with this website. We can't do that. So just put the marker there. So the marker's now here. We scan all the items to the right of the list, to the right of the marker, sorry. And if the item is smaller than the marker, then we swap them. In this case, the smallest item is 78, and 78 is not smaller than the marker, so we do nothing. We do nothing. So the marker gets incremented. Now, we do the same again. We've got 78, and we scan the items to the right of the marker. They're 89 and 83. If 83 is the smallest, if 83 is smaller than 78, then we swap them. It's not, so we do nothing. And I've lost all my... So then the marker comes to 89, and we look at all the items to the right. There's only one item there, which is 83. If 83 is smaller than 89, we swap them. And in this case, 83 is smaller, and hence the list is now sorted. Okay. Okay, so here's the algorithm. Here's the algorithm or the pseudocode for selection sort. So we initialize the unsorted list. We initialize the marker. So you remember in the previous one, the second step was we initialized a second list. In this case, we do not initialize a second list. Therefore, we don't need twice the memory. So this is the advantage. So we initialize a marker. We loop across the list. We find the minimum item to the right of the marker, swap the minimum item with the marker, and advance the marker. So in here, this isn't actually strictly true. It should say if the item is smaller, if the smallest item is smaller than the marker, then we swap them. Okay? So that's that. That's selection sort. The variable marker is used. I'm going to go through the code here now in a wee second with you. Just want to draw your attention to a few things. We've got a variable in the code now called marker. And the variable marker is used to store the index that will contain the next item to be sorted. all items to the left of the marker are already sorted. So if we look back here, the marker is here, all these items are sorted. Everything to the left of the marker is sorted. And then once the marker moves to here, these are all sorted. And down to here, these are all sorted. So we don't even have to look at those. All items to the left of the marker are sorted. All items to the right of the marker are yet to be sorted. The variable index of min is the index of the smallest item to the right of the marker. I'm going to go through the code now in a second. And the variable index of min, that's the one where we scan all items to the right of the marker, we find the smallest item, and we assign that to a variable called index of min. The item at this position will be swapped with the item marker. This is the heart of the algorithm. The item at this position will be swapped with the item at the marker. So let's have a look at the code. Let's have a quick look at the code. Selection sort. Okay, so here I've got this code now. It's all labeled. It's all labeled with the same pseudocode as we showed you at the start. So we'll just run it here for the start. We've got our initial list. We've got our marker, and the marker is set to 0. So basically, what the marker is the index of the index of the first item on the list. So we'll run it just to show that it actually works. And you can see there now we have our sorted list. So we'll just have a quick scan over it here. Run. Nicer. And we have our initialize the list, initialize the marker, and we have a while loop here now. We'll go into that. While the marker is less than length. So what's going to happen is the marker down here, marker gets incremented. So as long as the marker is less than the length of the list, we will keep cycling over. We'll keep sorting. So here now we assign marker to the index. We assign marker to index of min. Marker 0, so we're making index of min 0 to start with. And then we're going to, what we have here now is we have a for loop. We have a for loop here now, and the for loop now is going to look at all items to the right of the marker. You notice here now, marker plus 1. What that's doing is adding 1 to the marker, so that all the items to the right of the marker, we look at the items to the right of the marker. We don't need to look at the items to the left of the marker because they're already sorted. So we're scanning over all those items. So we're starting at item number 1, and we're going to finish at the last item on the list. And then here, what's going on here now? If which one of these is the marker? If Lj is less than the index of min, then index of min equals j. So what that there is doing now is checking to see if the index of min, if the first item in the list which is the marker, is less than this item here, which is going to be 6 in the first pass. So we'll have a look at it. So j is, you can see there, j is 1, because we're only interested in the items to the right of the marker. So that's 6. If 6 is less than the item that's our marker, which is L, which is 9 in this case. if 6 is less than 9, then index of min equals j. So j is the index of the smallest item, which in this case it's 6 so far. So that's doing basically with this part, what that code there is doing is finding the smallest item on the list to the right of the marker. That's all it's doing. We can't use min. We can't use the min method that we used in the previous algorithm. Why not? Any ideas? It would include all the numbers, and we can't do that. This is the whole reason why we've got this bit of code here now. Very good. So this bit of code here just checks all the items to the right of the marker, and assigns the smallest item to the variable index of min. And then, do we recognize this? Do we recognize that code there? What is it? I heard somebody say it. It's the swap algorithm, exactly. So we swap them. So as you can see up here now, we've looked at 9 and we've looked at 6, and we're going to check now to see if 6 is smaller than 9. We've done that here. If 6 is smaller than 9, then we swap them. Well, that's not actually true. We've got to go through this here until we find the smallest item. The smallest item is 4. So this we could run through this. Index of min. You'll see here. Where is it? Index of min. Index of min. There. That's the reason. Index of min is now 1, and on the first pass, index of min should be 3 because it's the index of the smallest item to the right of the marker. So if I just fly through this very quickly, you'll see index of min will be 3. There we go. And then once we've got to there, once we break out of, got to keep going through this. I'll just break out of it. So the index of min is 3, so the smallest item is 3. The smallest item is 3, and we'll swap the smallest item with the marker. So that's what we're doing. We're swapping the smallest item with the marker. So you'll see here now that these will get 9 and 4 will get swapped. Nine is the marker. 4 is the index 3, item index 3, which is 4, gets swapped with the marker. You can see here now that 4 has just got moved over, but we haven't replaced it. We haven't replaced that item with 9 yet. And then we increment the marker. And that goes on and on and on. Now, don't worry too much. Don't worry too much if the code seems like rocket science to you. You won't be expected to write that. You might be expected to recognize it. You might. No, this is me speculating. I don't know. The reason I don't know is because it's never come up in an exam. So I'm just speculating. The kind of question that they could ask is they could ask you to identify the swap algorithm. That'd be a good question. A good question to ask. What's the significance of lines 15, 16, and 17? Something like that there. Can you identify the swap algorithm? What's going on in line 10? You could explain that. And if you have a reasonable level of Python, you mightn't even need to know too much about swap algorithms to be able to answer that question. But it's a good idea to have a good grasp of it. Okay, so that's that algorithm. So let's have a look at a wee challenge for us, because I'm sure you're fed up listening to me. Okay. So, this table here now shows what's going on in the algorithm. This table now shows what's going on in the algorithm, and you can see here this is the first pass. This is a seven item list, and this is what it starts off as. Okay. So in the first pass, 9 is the marker, 4 is the smallest item. So 4 is smaller than 9, so they get swapped. So in the second pass, the marker now becomes 6. It gets incremented. 5 is the smallest item to the right of the marker. 5 is smaller than 6, so they get swapped. Now, what I want you to pay attention to, because this is the challenge that I'm just setting for you. You're going to need a pen and paper to do this challenge. So what I've got here is I've got a wee table here now that identifies what the marker is, and it identifies what the index of min is. Okay? So you're going to have to do this yourself with the next challenge. So on the third pass, the marker becomes 10, and the index of min is 5. You see that? It's the index of the smallest item is 5. Okay? If 6 is smaller than 10, we swap them, and that's what happens. Marker gets incremented, the index of min becomes 6, and if 7 is smaller than 9, we swap them, which we do. Marker gets incremented. Next pass, if 9 is smaller than 8, or no, there is nothing smaller, so there's the index of min. The index of min will be 9, will be 6, sorry. And, well, it's actually, we don't have an index of min in this case. And then we increment to the next one, the next item in the list. The index of min is 6, and they get swapped. And then in that final pass, nothing actually happens. Okay, so on that now, I have a challenge for you. So I've given you a list here now. I've given you a list. The list has 1, 2, 3, 4, 5, 6, 7 items. Okay, we've got 7 items. This slot is for you to tell me what the marker is, and this slot is to tell me what the index of min is. Index of the smallest item in the list. All right? So, what I want you to do is fill in the blanks. Fill in the blanks to start with. All right? So what does the list look like after one pass? And the next pass, and the next pass, and the next pass. So as you can see there now, I've made it slightly handier for you by highlighting what the marker will be in green for each pass. Okay? So what I want you to do is, based on selection sort, fill in the blanks. All right? Pen and paper, folks. You done, folks? Happy? Handy enough? If you want to fill in there on the right hand side, what's the value of the marker and what's the index of min? So the index of the min is the smallest item to the right of the marker. Is the index, sorry, it's the index of the smallest item to the right of the marker. We done? Yeah, okay. So let's have a quick look. Let's have a quick look at this. This is the type of question that came up last year in the exam. Okay, we will. Okay, so shout them out here. What goes in here? 2. What next? 8. 5. 7. Why 7?
Because you switched it with the 7 was the marker and 2 was the minimum value there, so you switched the positions.
Good stuff. Very good. And then
4, 6, and 3.
4, 6, and 3. So what's the marker now on the second pass? 8. And what's the index of min? 6. 6 is the index of min. This is the one that would catch you out because it's the actual index. It's the index here, right? The index of the smallest item to the right of the marker. All right, it's the index of the smallest item to the right of the marker. Okay, so we've now got 8 as our marker. The index of min is 3. What happens in the next line?
2 and 3.
And 3. Good.
And 5.
7, 4, 6, and 8. So what's happened here now is 8 gets swapped with 3 because 3 is smaller than 8. Okay, so what is the marker? 5. And what is the index of min? 4. That's exactly right. Okay. Okay, so everything to the left of the marker is already sorted. So they're not going to change. 2, 3, 5. So this is now 4.
Isn't that 5 meant to be a 4 because you switched it around?
Oh, okay, sorry. You're right. Good man. So we've got 4. Good man. So this is now 7, sorry. Okay, so what goes here? 5. And then we've got 6 and 8. So what's the marker?
7,
And what's the index of min?
4,
4. Okay. Then we've got our 2, 3, 4. And is a swap taking place here? So what goes here?
5.
And
7
then 6 and 8. And what's the marker? 7. And what is the index of min? 5. Whoops. And then we've got 2, 3, 4, 5, and what goes here? 6, because 6 is less than 7, so we swap them. So then 7 goes there, and 8 goes there. And the marker is 7. The index of min, there is only one item to the right, so it must be 6.
Not 5, after 7 is the lowest value.
7 is the lowest. Aye, but we only look, remember I showed you in the code earlier, we only look at items to the right of the marker. Aye, so then we don't, once we get to here, we have our marker is 8, but there are no items to the right of the marker, so we don't have an index. We don't have an index. So, well done, folks. That is, so for your own viewing, you should now be well fit to answer question 14A in last year's exam paper. 14A. We're out of time as far as search and sort is concerned. I have plenty more stuff there on that PowerPoint to take you through insertion sort. Insertion sort is the next question. Insertion sort is question 14B, and this would be, in my opinion, this would be a much more intuitive sorting algorithm, and I've got all the code for that up there as well. So, and I've got another challenge, it's the same thing. Okay, so we're out of time on that. So we're going to take a break now for 10 minutes. There is a drink for you in the canteen, as far as I know. A snack and a drink in the canteen for you now. So, judging by previous years that I've done this, there's no bell here. So nobody's going to be coming telling you to come back here for 10 past 11. So you just need to take it upon yourselves to be back here for 10 past 11. All right? So, take a break now for 10 minutes, and we'll see us back here at 10 past 11. Okay, folks, welcome back. This session now, what we're going to do, we've got about an hour and 15 minutes for this session. This is the question C, Python exam that you have. So basically what I'm going to do is I'm going to go through last year's ordinary level Python exam and then go through last year's higher level Python exam. All right? So there's a few handy spots that you can pick up marks with these exams. So that's good. So I'm just going to go through this with you. Now I have shared the folder with you. I don't know if you're able to access that folder. Were we able to access it? The starter code for this session is in that folder. I'll show you the folder. So where are we? Here. This stuff here should be in there. Where do we just go to the actual folder that I've shared with you? So this is the folder that I've shared with you here, if you have a look. And we'll go in there, and under 2022, if you go in there, all the exam papers for last year are in there. Now I've got the starter code here for the first bit, OL16A. So that's for the first session. If you want to double click on that to open that, that'll get you the starter code for this session. Don't worry if you don't have it. All I want, if you don't have access to this folder, that's fine. What we can do is you can go to examinations.ie, and we'll go to examination material archive. Tick this box, choose exam paper, choose 2022, choose leave insert, and choose computer science. And in there, what we're going to be working on here is ordinary level C EV for English version. So you'll click on that, and that will get you the starter code that we want. Now the starter code, the only problem with doing it this way is we have to copy and paste this, and that's going to copy all of these numbers in. So you're going to have to delete all them, and the indentation is going to be off. But I'll tell you what, I'll just copy that in, and I'll do it that way, because some people might not have access to this. File, new, pop this in, paste, and I'm going to save this, save as 2022 live. Okay, so now there's going to be a problem with this because all of these numbers have just copied on. So we need to get rid of all that. So I'm just going to delete all them. And on line 13 there, we have, I'm just going to have to pull that back there, and we have any indentation? We do. We need line 16. We need to indent that. Just press tab there. Okay, so I'll give you 2 minutes to get that done. Do we have access to the folder that I shared with you? It should be emailed to you. You don't have access to it, so you can get this on the way I'm only after showing you there now, and just do it that way, and then we'll have a look at the exam question. So I'm going to give you 2 or 3 minutes to get that done, and then we'll have a look at the exam question. If you're using your phone, you could use REPL or something like that. REPL or some online version. I'm using Thonny. Just run your code to make sure that it works first. The only issue that I would imagine that you're going to have possibly is the indentation here on line 16. Anybody having any issues there with your file? We're laughing. We're okay? No problem. Are we ready to go? Yeah. Okay, so let's have a look. Let's have a look at the question. There's a few wild handy marks that can be picked up here. So the question reads, open the program called question 16a. So you'll be given a file, probably a memory stick or something on the day. The source code is shown and described below. Before making any changes, you should save your file. Save your working copy of the file in the format examinations number. So you've got to stick in your exam number here at the start. Okay. So enter your examination number in the space. As you can see here now, we've got a space provided here on line 2 for you to enter your exam number. No marks going for that, I don't think. Okay. The program above is to simulate an automated shop. The aim of the program is to accept the name of the user and then to ask the user to choose what item they would like to buy. The user will select the number of the item they wish to buy, and the program outputs a message confirming the item they chose. So let's run that to see that does it work. So what is the name? I'm going to say Gary, and we get this printout. The printout says items available 1. Enter the number of the item you would like. So I'll enter 1, and you bought a book. It appears to be working. So that's fine. Let's have a look at the questions. Okay, make the following changes to the program. Insert a comment in the appropriate place to say user enters first name. So what are they asking me to do? They're asking me to enter a comment that says user enters first name. So how do I put in a comment to start with? Well, here's the first tip for whenever you're doing an exam. we've already got comments all over the place on the code that you've been given. We've already got them. So we use this hashtag symbol for our comment. So we've been asked to insert a comment in the appropriate place to say user enters first name. So where does the user enter the first name? First name input there. So the user enters their first name here. We could put it here. So we put in hashtag and then paste that. We could put it there, or we could put it, probably a better place to put it, Control X, put it above here. Like that. Doesn't make any difference. You'll get the marks. And they're handy marks to pick up. Next question. Amend the program to ask for and accept the user's surname. Store the user's surname in a variable called surname, and when the program is run, the output may look as follows. So you enter your first name and then you enter the surname. So this is good. So basically what they're asking us to do is they're asking us to ask the user to enter their surname and pop it in here. So the good thing, tip number 2 for when you're doing your exam. We've already got the code to do this. They've given it to us. It's just putting it in the right place. So what you want to do is, see this line here, line 5, that's the code that we need. We're going to copy that, and we're going to paste it in here in line 6. And we're going to change that now to answer this question. So we want to get the users, we want to get the surname of the user. Surname, S-U-R. What is your surname? So what we've done here is we've created a variable called surname, and we're using the input method to take an input from the user and assign it to the variable surname. So let's run that to see does it work. So what is your first name? Mine is still Gary. And what is your surname? Gorman. Now, our output isn't correct though. It says hello Gary, and what we're looking for is we're fine so far. We're actually fine so far. We've got it all. We've got it all. So let's have a look. Yeah. What is your first name? What is your surname? Hello Gary. So now the next part, it says amend the program so that the user's first name and surname are printed when they are asked to select their item. So when the program is run, the output should look like this. So it should say, the change here now is it should say hello Mary Murphy rather than what it currently says, which is hello Gary. So how do you do that? Any ideas?
On line 8 after first name, just put the variable like a comma.
Oop. What is that? Sorry about that, folks. Just had a fire alarm. Fireman Sam came and put it out. So, where are we at here now? Just to recap on where we were at. What's your name again? Sorry. Shino. Shino just suggested that we put in surname in here as an argument in here in the print statement. So let's, in order to answer this question, it says, amend the program so that the user's first name and surname are printed when they're asked to select their item. When the program is run, the output may now look like as follows. So here we have, this is the change here. So what we want to happen is we want to print hello and first name and surname. So, and there we go. We've got hello, first name and surname. Let's test that to see does it work. First name, still Gary. Gorman. And then what we have here now is we have hello, Gary Gorman. So that's working. That's working appropriately there now. Okay. How you doing? So that's question 3 sorted. Question 4. Let's have a look at question 4. Amend the program so that items 2 equals ruler and 3 equals pen appear in the shopping list under item 1 equals book. When the program is run, the output may look as follows. So we're looking to print out this, and we're looking for it to offer the user the option to select ruler and pen. So this is basically a menu item here now. So let's have a look to see how this how book is printed out. So it's very simple. We've got 1 equals book written here in line 13. So basically I'm going to copy this. I'm going to pop it in here and here, and I'm going to change this to 2 ruler. And 3 pen. I think that's it. Just looking to print out this so we have 2 more items in the menu. So let's have a look to see how that works. We'll test it. What's your first name? And I have ruler. So we've got our menu now, and we've added ruler and pen to our menu. Okay, so that's that. If I'm going too fast, folks, just let me know, and I'll slow down. All right? Just need a wee minute to catch up. Happy enough? Okay. Okay, so let's have a look. Question 5. Amend the program so that a dashed line appears above and below the available items. When the program is run, the output may now look as follows. So we've got a whole load of dashed lines here. I'm just going to copy them. And a whole load of dashed lines here. So what comes to mind there now is we just need a print statement with a whole load of dashed lines on it. So let's have a look to see. We want it to be above book and below pen. So we'll go above book and we'll stick in a print statement. Print. And we've got to paste that in there. And there we go. Let's test that before we waste our time doing the next bit to see if this is correct and it actually works. So we'll just test it. What's your name? And there we've got our dashed line there above book, and so that means that we can just copy this. Copy that. We'll just pop it in there and run that. And there we have it. So all we did there to answer question 5 is we put a print statement with a whole load of dashed lines on line 13 and a print statement with a whole load of dashed lines on line 17. That's all we did. Above book and below pen. And that's it. Hello.
Would you use marks if you just, instead of putting another print statement in the first one, you could just say it's a /n and then with the hyphens?
Would you look? Right. If it's the way the marking works with Leaving Cert Computer Science is, now I haven't corrected Leaving Cert Computer Science, but I've spoken to people who have, and any valid working solution will get you the marks. Simple. So if you've done something that works, you'll get the marks. And you're able to test that on the day. This is one of the only subjects that you know you're right when you leave the exam for that reason. So if you've got a valid working solution, consider it. You've got the marks in the bag. All right? Okay. How are we getting on there, folks? Happy? Content? Am I going too fast? No. Okay. So that is question 5. Question 6. Amend the program so that the correct message is printed if the user purchases a ruler or pen. When the program is run, the output may now look as follows. Enter the number of the item you would like. 2, you bought a ruler. Okay. So we've got to do that. We've got to do this for a ruler and pen. So let's have a look to see how do we do that. So on line 19, we've got another input statement, whereas enter the number of the item you would like. And that is, you can see here now, we've got int here. What we're doing here now is we're casting the input statement. We're converting it from a string to an integer here. That's what this method, this int method, does. So we're asking the user to input the number of the item they would like to buy. So let's see how it works first. We already know that it works. If you type in 1, it says you bought a book. So what we want to figure out is, now is how do we, if the user enters the number 2, how do we get it to say you bought a ruler? If shopping item, copy, equals 2, print, you bought a ruler. Good. Let's test that. And now we've got enter the number. So we've written the code now for you bought a ruler. So I'm going to put in 2 now to check to see is that correct. 2. You bought a ruler. That works. Is there any modification that anyone could suggest that we would make to that code to make it a wee bit better. Now, you'll get the full marks for that. You will, 100%. You'll get the full marks for that. elif, exactly. elif. elif. Now, what's the difference? You might say, what is the difference? To the user, there'll be no difference. But what will happen is, if you have this as an if statement, the program will check to see if the item is 1. If the item is 1, it will print this. But if it's an if, it will also check to see if the item is 2 when there's no need. elif. To the user, or as far as the exam is concerned, you'll get the full marks if you put in just an if statements. An if statement, that'll be just fine. So the elif is the way to go. So we know. Let's test that to make sure that works. And we'll put in 2 for rule again, and that works. So all we have to do now, we've tested to see does that work. We'll copy this, and we'll paste that in here. elif, we'll change this to 3, and we want 3 to be pen. And let's test that. It's important that whenever you're doing the exam, folks, that you test and test regularly. All right, test as you're going along over and over again to make sure that you're doing things right. First name. And we want to test now to see does 3 work. And 3 works. You bought a pen. Okay. Okay, so let's have a look now to see what, this is the last question now in the ordinary level exam. Amend the program to deal with invalid number entries. If the user enters any number other than 1, 2, or 3, they should be presented with an error message. When the program is run, the output may now look as follows. Enter the number of the item you would like to buy. So they've entered an invalid number here, 5, and you should get invalid choice, goodbye. Okay, so any suggestions? Don't be keeping it a secret now. Else. Let's try else. So where do we put that? Below the elif. So I'm going to go else. Else. Print. Invalid. Invalid entry. Entry. Goodbye. Let's test that. So, your name. So let's put in 5. Invalid entry, goodbye. Okay, so why did we use else at the end? Why didn't we go elif shopping list equals 5, equals 5?
Because it's only asking if it's not in the range. So instead of being an elif or like a specific value, you just say else. It's just anything else outside of 3, 1, 3.
Very good, very good. So we're basically, this is a bit of what they call validation. So if you enter any value that is not 1, 2, or 3, then the else will kick in. And then anything other than 1, 2, or 3 will be printed. This line here will be printed out. Okay, so that's super. That's the ordinary level exam paper. So the important takeaway that I want you to take from the ordinary level paper here now is test and test and test and test over and over and over again. And whenever you get an error, we'll have a look. We'll do some errors in the next one just for the crack, on purpose, just so that you can error messages, because sometimes they look like rocket science. level. Part C 2022 and do the same processes as we did before, and just and there's a bit of indentation that needs to be sorted out for this one. Question C. Can I just draw your attention to this for a wee second? Whenever you're copying and pasting everything in, you'll see in the exam paper there, I'll just zoom that in a bit. You'll see in the exam paper there that we've got a for loop here, and everything from here down to here must be indented underneath the for loop so that it's included in the for loop. So you just need to be careful of that. Then this line here, on line 16, that needs to be indented as well, just using the tab key there. And just test it to make sure that and once you have it working, then we'll carry on and we'll have a look at the exam paper. Just let me know when you're ready there, folks. We're good to go, folks? It's working? Okay, so let's have a look at the question here now before we go any further. Okay, so the question reads, open the program, question 16A from your device. The source code is shown below. Before making any changes, you should save. This is the same as the ordinary level. You've got to save the file using your exam number. I don't know, you mightn't have your exam numbers yet, but you should have them before the exam comes. Enter your exam number in the space provided in line 2 here, there. Okay. The program simulates the rolling of a die 100 times, or a dice. The result of each throw, if each roll or throw, called throw result. There it is there. Throw result. There. Each of the 100 results are appended to a list called results as they are generated. So we've got an empty list here called results, and all the throws are, as you can see here in line 12, results.append throw result. So what's happening there? Just to clarify, randint here, what's that? What's that all about? Well, what we have here on line 3 is we're importing a library known as random. What the library is called random, and what we want to do is we want to generate a random integer. So we're importing the random integer part of this library, the random library. So what we can do, the randint has a method called randint, and what we can do is what that will do is that'll generate a random number between 1 and 6, depending on what arguments you put in here, 1 and 6. So if you wanted it to be one, say it was two dice, you could put in there 1 and 12. So that's not part of today. So basically, this will generate a random number between 1 and 6 and assign that number to throw result. Okay. So the throw result then will be a number between 1 and 6, and that gets appended into the results list, and currently that's empty. So, and this happens 100 times. So this results list here will have 100 items in it at the end of the list, at the end of the program. Whoops. So the results of each roll or throw is stored in a variable called throw results. Each of the 100 results are appended to the list called results as they are generated. The program also contains code to keep track on the number of times 1 and 2 are rolled. These are stored in a list called frequencies. So we've got a list called frequencies here that's already populated with zeros. 6 zeros. Okay, so what's it doing here? If throw result equals 1, frequency 0 equals frequency 0 plus 1. So what we're basically doing here now is that the first item in the list is getting incremented by 1 if the dice rolls 1. If the dice rolls 2, then the second item, index item 1, gets incremented. Okay, so this could be quite confusion here, probably because of the indexing. All right, that's the first item in the list, that's the second item in the list, and what we're doing is we're incrementing those items in the list when they appear in result. Okay. Okay, so let's have a look at some of these questions. Well, let's test to see what the program should look like first before whenever we print to the shell or run the program. So what we get is we get an output saying DICE simulation program, and the output is a list with 100 items in it. So that's fine. And the items are all between 1 and 6. Perfect. So that's fine. We know what's happening. So, question 1. Currently, the first line of the program output is DICE simulation program. So that's fine. That's it there. DICE simulation program. And then we've all our results. So every time, don't be thinking that your results have to be the exact same as this. Because of the random nature of this program, your results will be different. Change the program so that the first line in the output is DICE simulation analysis. I'm just going to copy that. DICE simulation and analysis program. So what we've got to do, we want this line here to be changed from what it currently is to this. And we'll pop that in here. So DICE simulation program, we want it to change from DICE simulation program to DICE simulation and analysis program. Let's run that to see if that works. And there we go. So that's fairly straightforward. Second part. Insert a new line of code at the end of the program to display the list of DICE frequencies. When the program runs, the output should look as follows. So we should have printing out the word frequencies, and then we should have the list frequencies printed out. So let's have a look. So we have this list frequencies here. So we want to print that out. And we've got down here print results, and we want to say print results frequencies. Control C. I'm going to paste that here, and I'm going to change this to frequencies. Frequencies, and I'm going to change this to this variable name. Copy. I'm going to pop that in here, just so I don't misspell anything. Just copying and pasting it in. So let's test that. There we go. Frequencies. And there we go. That's it. That's working. That's working just fine. Okay. Let's look at question. We've done that. The frequencies list tells us that the number 1 has been rolled 14 times and the number 2 has been rolled 15 times. The frequencies for numbers 3, 4, 5, and 6 are not calculated by the program yet. This is the reason why they're all 0. So that's fine. That's fine. That's probably going to be the next question. So let's have a look at the next question. Complete the code to calculate the frequencies for numbers 3, 4, 5, and 6. When the program is run, the output may look as follows. So it's the exact same, except for we've now got numbers in here for 18, 13, for whenever the dice gets 3, 4, 5, and 6. In this case, the frequencies tells us the number 1 has been rolled 11 times, the number 2 has been rolled 23 times, number 3 has been rolled 18 times, and the number 4 has been rolled blah, blah, blah. You get the picture. Okay, so that's what we want to do. The beauty of this is they've already given us the code to do this. They've already given us the code to do this. So what is the code to do this? So we've been given the code to populate this list, the list of frequencies for number 1 and number 2. So basically what we want to do is we want to change this to be, we want to add to this to make it for number 3, number 4, number 5. Let's do number 3 first and check to see if we're correct. So I'm just going to copy that and I'm going to paste that down here. And what we want to do is we want to go elif throw result equals 3. 3. So this line here needs to change. So what we're doing here is frequencies 1, that's not right. We want it to be frequencies 2, the index item 2, so this is 0, 1, 2. So we're going to modify that to count the number 3s. So then frequencies, sorry, that should be 2. And this should be 2. So what we want to do is we want to increment, we want to add 1 on here every time we count a 3 when the dice is rolled. So let's test that. We don't want to go any further now without testing that to make sure we're on the right path. So there we go. We're now counting the number 12s. Now, here's something. Here's something that I'm not sure. I'm not going to spend all day now counting to make sure that is there 12 number 3s in there. So I'm just going to take this instead of rolling the dice 100 times, I'm going to roll it 10 times and then test it. So there now, I've rolled it 10 times and the number 3 appears in there 10 times. 1, 2, 3 times. So I know that works. So I'll put this back to 100 now. And roll that. So now we can see there that works. We're now counting the 3s correctly. I can now add in 4, 5, and 6. It should be the exact same thing. So I'm just going to copy these elifs. Copy. And I need one more. And what I need to do is I need to change all these to 1, 2, 3, 3, 4, 5. Change this to 3, 4, and 5. And let's run that. Now, they're not working. Oh, can anybody see why? Can anybody see why? Why is this not working for me?
Because frequencies, you number it as a list, but in actuality, there's like, for example, for the first one, frequencies for 0, there's no such thing as 0 on my dice. It starts as 1.
Oh, I get you. I can see where you're coming from. So basically what we're looking at here, what this here does here, what frequencies and the square brackets 0 does, is that looks at this list here called frequencies, and it looks at the index 0 item in that list. All right, so that actually does exist. The solution to this is way simpler. This is something that's going to happen in your exam if you copy and paste. Anybody else see it? Yeah, that's right. So what are you saying?
So just 1, 2, 3, and then after that it's just 4, 5, 6.
Good. Good. So we've got 4. We've got to change this to 4. Got to change this to 5, and change this to 6. So basically, what we're doing is we're checking to see in the first line if the dice scored 1. Then the next one, if the dice scored 2, 3, 4, 5, and 6. So this should work now. Okay, there we go. We've got it working. And if you want to test that again, if you want to test it and make sure that it works, we can bring this down to 10 and run that. You can see there 1 appears in the list once. 2 appears in the list 1, 2, 3, 4 times. 3 appears 1 2 times, that's correct. 4 appears once, 5 appears once, and 6 appears once. So that's not bad. Just a wee debugging tool there now. Code might be working, but it mightn't be logically correct. Like you can see there now that I made a logic error there a minute ago, but we're able to figure it out. Okay. Do you need a minute or two to finish that? Done? Happy? Okay. Okay. Question 5. Comment out the line that displays the list of individual results. When the program is run, the output may look as follows. So we no longer want to print the results. We don't want to print this here out. So this is just, basically what we're being tested on is your ability to comment something out. Can you do it? So how do we comment something out? Hashtag, exactly. So it's line 29, results, that's where that gets printed out. So we've got to just comment that out with a hashtag. Let's test that. There we go, as requested. Okay. We're getting there now, folks. Question 5. Extend the program to display the frequency of each number in a tabular format as shown in the sample output here. So we want to display what's in the frequency list down here like this, dice frequency, and then we want a whole lot of dashes, and then we want these. We want this is basically the index plus 1. The index for this one would be 0, and so we'd want to increment that. And over here we have the values, these values here. So, have we any idea how we might approach this? I don't have a clue how to do this. Anybody able to help me? How do we get all the values out individually out of a list? Use what? We could. That would be a valid solution. We could use square brackets to individually. We could have a print statement for each one of these lines, and that would solve the problem. Let's do it for the crack. Let's do it a few different ways. So you're using square brackets. So I'm going to do a print statement. You're going to have to help me with this because I don't know how to do it. Print. So what goes in here? So first line is going to be dice frequency. Okay. Dice frequency. Let's test that to make sure that works. Dice frequency is printing. That's perfect. So the next line, we want print, and we want our hyphens. We'll test that, and that's working. So what's next? So, what do we do now? How do we get the value, the first value in frequencies? There. How do we print that out there? So we're going to need a print statement. Print. Then we're going to need 1. And we're going to need a tab, I would say, /t. and then we're going to,
Wouldn't be advisable to put that in //t for line 32 and 33.
say it again.
You know, if misaligned the value then.
So what we want to do is we want to pop it over like here. All right? So that we'll see what it looks like, and we'll change it if it's not right. I'm not sure. I've never done it this way before. So let's figure it out. This is what you're going to have to think on your feet in the exam. Try it. So what goes in here now? What we want to do is we want to get the first item in the frequencies list. So we've got a frequencies list here. We want to get the first item in it. So how do we access the first item in the frequencies list? Frequencies, did I spell that right? And then square brackets, and we'll want index item 0. Let's try that. There we go. So now it's popping over there onto the right hand side. Okay, so you're right. It's a wee bit over to the right. That's not really what they're testing. Like what we could do here, if you really wanted, we could just pop in a handful of spaces there and run the same thing. That'd be fine. So I just put in tab. You can put in whatever you want, and that'll work just fine. Okay. So we can do that now. We can copy this. We can copy this, and we can. There's 1, 2, 3, 4, 5. We need one more, and we can change this to 2, 3, 4, 5, 6, and we'll change this to 1, 2, 3, 4, 5. Let's see, does that work? And that works perfectly. Perfectly. If you do that in the exam, you get full marks. Full marks. Okay. Is there a handier way? Is there a different way that we could do it? Okay. I am going to comment this out. This is a very good, valid solution, 100%. So there's another way we can do it. We can use a for loop here, and we can go for item in range, and we want this to be the range of frequencies. So we can go range 6 because we know the length of it's 6, so we don't need to go messing about. Range 6. So what I want to do is I want to cycle through all the items. What do I just go back over here? I want to cycle through all the items in this list and print them out one by one. Okay. So what I can do is instead of having 6 separate print statements, I can just have the one. So I can go print, and what I want to do is I want to print the index. I want to print the index. Well, this isn't exactly the index, is it? It's one more than the index of each item in the list. So what I want to do is I want to print. So what happens in a for loop? Whenever we run this for loop here now, this part of a for loop here is a variable, and this variable here, for the first iteration of our loop, the value that gets assigned to that is a value between 0 and 6. Not including 6. So it's going to be 0 first, then 1, then 2, then 3, then 4, then 5. So 0 is going to get assigned to item first. So I want to go item plus 1. Item plus 1. So that's the first thing that I want to print. Then what I want to do is I want to print out frequency 0 on my first iteration. Control V. And it's not going to be frequency 0. It has to be frequencies item. So item is going to be, in the first iteration, it's going to be 0. So I want the zeroth, if that's even a word, basically the first item in the list to be printed here. And then in the second iteration, I want the second item to be printed here. So let's test that to see if that works. So it's working. That's working. We need a space between them. So I'm just going to put on a couple of spaces. We could put on a tab either and try that. There we go. So there's two different ways you could do it. This way here is just less code. This way here that you did it there now might be easier for you to understand. Good solution. I never thought of doing it that way. I like it though. I like it. Okay. We have 12 minutes before lunch to get this finished, so let's motor on. That's question 5. Question 6. Extend the program so that it determines and displays the number that was rolled most often along with its frequency. For example, if the output below the number 5 was rolled most often 25 times, you can ignore the possibility of ties. So if there's two of them that were rolled 25 times, don't worry about it. It'll be grand. When the program runs, the output should be as follows. So 5 was rolled the most often 25 times. So you can see that there now. So this is what we're looking to do. We're looking to find the largest number in a list. Okay? Now, there's a wild handy solution for this. And this is something that possibly that you might not be aware of. Just want to see if I can find this file. This is a file that you're going to have in your you're going to have available to you in the exam. Leave insert computer science revision day. Python revision. There we go. So this file here, this is called the Python revision guide. Have you ever seen this before? Anybody seen this before? Yes, one of us. Okay, this is important. This document here will be available to you on probably a laminated sheet during the exam. All right? There's a world of information on here. All right? You've probably you've done your project. You've a fair bit of experience using Python now. You know now that there's methods to do almost anything to do with Python. So this is a reminder of all those methods. You could sit down in your exam now and spend 20 minutes writing a for loop to find the largest item in a list when you don't need to. You've got this available to you in your exam. You'd probably be thinking to yourself in the exam, is there a method that automatically finds the largest item in a list for me? There's bound to be. So let's have a look. So what I've got is over here on the right hand side, I've got list methods. So I'll have a look in there. List.append, list.extend, list.insert. None of these kind of jump out at me. List.count, list.sort, list.reverse. Now none of them kind of help me in any way. So let's have a look at these built-in functions. So I'm looking at here now, and I'm looking min and max. That one there looks like it has potential. Returns the maximum value in L. Returns the maximum value in L. So whenever they say L there, that suggests to me that they're talking about a list. So it returns the maximum value in a list. We might be able to use that to solve our problem. All right? You can look there now. There's loads and loads of different methods in here that you might be able to use in the exam. What you want to be doing between now and your exam is get used to looking up this table. Get used to looking up this table because that's the only thing that you have available. This is your textbook that This is basically your cheat sheet that you can that you have available to you in the exam. You have this. This will be handed to you when you do the exam. Okay, so let's try this out. Max L. So if we put in max and then put in the name of our list in there, we should be able to get the largest item. We should be able to get the largest item in the list. So back to the question. The question asks us to print out 5 was rolled the most often 25 times. So we need a print statement. We need a print statement. So let's go down here. Print. Print what? So what we want to do is we want to find out what is the largest, what's the item that gets printed out. So what gets returned here? Wait a wee second. Where am I? So what gets returned here? So whenever we look for max, returns the maximum value in L. So does it return the maximum value? So let's have a look to see what it actually does. Print max. And I'm going to type in frequencies here. Max frequencies. So let's test that to see what that does. So 20. So it actually prints out the value. It actually prints out the value. So that's useful to me. So I'm going to go back here and I'm going to go, it was rolled out. Copy that. And I'm going to put that in first. So I'm going to have a Control V. And then I'm going to put in here times. So this is probably going to solve my problem here for me 25 times. It's going to print it out 25 times, but it's not solving me what number was done. What number was done. So let's run that. So was rolled 24 times. Okay. So what I want to do is I know that 24 in this situation, I know that 24 is the number of times that 4 was rolled. That 4 was rolled. But how do we get 4 in here? How do we get 4 in here? So what do we know about 4? 4 is well, it isn't actually the index. 3 will be the index because we've added 1 onto all of these. 3 will be the index of the largest item in this case. So what I want to do is I want to search my list to see what is the index of the largest item in this list. So I wonder, is there a method for that? What's the index of the large, or can we just search? Can we just simply search a list? So have a look here now. This is I don't know for sure what the story is. So I'm going to have a look at some of these methods that are available to me. Insert doesn't sound right. Remove, no. Clear, no. Index. Let's have a look at what index does. Index returns the position of the first occurrence of X in a list. Okay, that could be useful. So if we put the value that we want to find in the list in there, then we can search for it. That might work. Don't know. We'll try it. So, okay. So how do I do that? So what I want to do now is I want to, let's have a look to see what that looks like. List.indexX. So here I'm going to have to go, the list is called frequencies. Frequencies dot index, and then how does it look? Frequencies dot index, and then brackets, and then the value that we're looking for. The value that we're looking for. The value that we're looking for goes in there. So we're looking for the max frequencies. Control C, pop that in there. So this is an absolute mouthful here now of a line. Print frequencies dot index brackets max frequencies, and then we need a comma, and then was rolled that often max frequencies time. Let's see if that works. That's a lot to chew on. 2 was rolled the most times, most often 19 times. 2. Well, that's not right, because 3 was rolled 19 times. What's going on here? Why is this not working for me? Two was rolled the most times, 19 times. So we're finding the right thing. We're finding the right value. But we're not, what we wanted to be printing out is 3 was rolled the most times. So we have a problem here. What's going on here? The index value is 2. So what do we need to do to make it 3? Plus 1. Superb. Plus 1. Let's try that. 2 was rolled the most often 22 times. Now it's working. Let's run it a few times to make sure we're right. 6 was rolled the most often. Yes, we're onto a winner here now. 3 was rolled 23 times. That's perfect. Super. Okay, that's working. Now that's an absolute mouthful of a line there now, 44. Absolute mouthful. Let's see if I can tidy it up a wee bit. So basically what I'm going to do is I've used max frequencies twice. I don't want to. Who wants to do that? Nobody wants to do that. So if you're using the same code over and over again, that's you need. I'm going to create a variable called largest. Largest equals large e. St even might be close to it. So just instead here I'll go max frequencies. Max frequencies. So basically what I'm doing there now is I'm getting the max frequencies and I'm assigning it to a variable called largest. And instead of having max frequencies in there, I'm going to change that to largest. And I'm going to change this to largest. Let's test that. And that's working. Okay, that's working. There's a lot that fried a lot of brains. Fried mine a wee bit too. The last thing now is extend the program to display a horizontal bar chart of the frequencies. The number of asterisks in each row should correspond with each frequency. For example, in the output below, there are 8 asterisks in row 1 because the frequency for the number 1 is 8. So they're looking for us to print out, this is a bar chart. So if there's 8, the dice was rolled 8 times. So we've got 8 asterisks. Each asterisk can be printed using a single print statement there. So we can copy that. So with this end equals nothing, equals an empty string. So multiple print statements on the one line. Okay. When the program is run, the output of the program will look as follows. So we're gonna look at it like that. So what we want to do is we want to cycle through each item in the list and print out. If it says 8, we want to print out 8 times. If it says 12, we want to print it out 12 times. So I'm going to do this fairly quickly because we're going into our lunch break. Okay, so let's have a look. This is the handiest way now that I could think of. So we're going to go use a for loop. For item in frequencies. You'll notice here that I've put in the name of the list that we're looking in this time. This is different. What'll happen now for this type of for loop is the value in the list, each value in the list will get assigned to this variable. So what I want to do is I want to print out, I've got this print statement here, Control V. Okay. So I want to print this out, but I want to print this out a certain amount of times. So what I'm going to do is I'm just going to multiply that by item. Multiply the asterisk by item. Let's see, does that work? And we've got a whole load on the one line. So that's not working for me. So what I want to do is after I've printed out the number of asterisks, all I want to do is go print, and say print nothing. And there we have it. So 1 is rolled 16 times, 5 is rolled 8 times, and that's it. That's the simplest way that I can think of. There are a few other ways that I could show you after break, but there's one other way I'll show you after break. And we'll take it from there. Now, that was heavy enough going, folks. So if your head's spinning after that, I'm not surprised. All right? We're going to take a break now for half an hour. So if you want to scoot over to the canteen, we'll be back here for 1:05. All right?
Just gonna chat away.
All right, folks, welcome back. The last hour of our session now, we're going to 2 o'clock, will be on computational thinking, and this has featured on every exam paper so far, so it's very likely to appear again. There's a couple of questions last year as well on different computational thinking aspects. So what is computational thinking? It's a way of thinking that we use for problem solving, and it's particularly useful in computing. There are 4 pillars of computational thinking, and the way the questions will be presented to you in the exam will be along these lines. So we have pattern recognition, abstraction, decomposition, and algorithmic thinking. So we'll go through different questions from the exam over the last couple of years to have a look at this. Now, there's some of these things you might have done before. Algorithmic thinking, you maybe done flowcharts or pseudocode or stuff like that there to develop algorithms. So you've already done a lot of this stuff, and you just mightn't know that you've done it. All right. So pattern recognition. What is pattern recognition? Pattern recognition is identifying patterns. Identifying patterns is key to solving problems. So we need to be able to find patterns and things to help us solve problems. A lot of the time, if we can identify a pattern in a problem, we can solve the problem a lot more quickly than we would have been able to do otherwise. So, for example, this is just an example I got off the internet. When baking a cake, every cake has a pattern in how the cake needs to be baked, and each cake needs precise quantities of ingredients. Ingredients get added at specific times. Each cake will bake for a specific period of time. So there's a pattern. So let's say, for example, you're creating a cookbook. Then your cookbook could have each recipe for each cake, for each page. It could be split. Each page could be split up into 3 sections for ingredients, timing, and ingredients get added at a specific time. Each cake will be baked for a specific period of time. So you could have that, so that the layout of your cookbook would be uniform throughout. So that would help solve that problem. So here's one that appeared in 2001, not last year, the year before, question 13. So this is one of the short questions. So we'll try and make this a bit more of a discussion, as soon as it's late in the day and we're probably a bit tired. So the first character in the routing key. So basically this question here is about error codes. The first character in the routing key must always be a letter, and the second and third character must always be digits. Every character is a unique identifier, and the unique identifier must be alphanumeric, i.e. either a letter or a number. So we've got our unique identifier here. So every character must be either a letter or a number. And over here, first character must be a letter, and the second and third must be digits. So the question as it was put in the exam in 2021 was, explain why each of the following are not valid error codes. So we'll have a look at the first one. What's your name? Park. Do you want to have a look at the first one there and see if you can figure out why the first one is not? They're all not valid. They're all not valid. So why is the first one invalid? The first two are both letters. Very good. So this is a letter. So that invalidates it straight away, because the second character there must be a digit. So, what's your name, sorry? You? Jaggy. Jaga. Can you explain to me, have a look at the second error code there and see if you can figure out why that is invalid.
There's 4 digits are like numbers or keys or keys.
Exactly. Simple as that. And then What's your name? Saranj. I'm going to forget all your names, folks, so I'll be asking you again in a wee minute. Saranj, can you tell me why is the third one invalid? And anything else? It's meant to be a letter. Exactly. So the 8 is meant to be a letter, the X is meant to be a digit, and the T is also meant to be a digit. Okay, so that's the most recent. That's one of the short questions that came up in the exam a couple of 2 years ago. We're going to have a look at one of the longer questions that came up in the Leaving Cert 2 years ago. So this is the matchstick game. I have a pile of chips here. I'll use that to help explain this game. Okay, this is a bit of a mouthful, the explanation for this game. So if you don't understand, I'll give you a couple of minutes to chew on it, basically. So we'll have a read of it first. So we have a two-player game. A two-player game where, like say, chess or drafts, where you take alternate turns. All right? A player must remove 1 or 2 matches. So we've got a stack of matchsticks. A player must remove either 1 or 2 matchsticks from the pile. A player who lifts the matchstick, the player who lifts the last matchstick wins. So, so basically, the point of this exercise here now is to fill out a table to say whether you're working off a winning position or a losing position. So anyway, let's read. Winning and losing positions are defined in terms of the number of matchsticks left on the board. A winning position is a position from which a player cannot lose if he makes all the optimal moves until the end of the game. For example, 2 is a winning position because if the player whose turn it is makes the optimal move, which is removing 2 matchsticks, then they win the game. A losing position is a position from where the player cannot win, assuming their opponent makes all the optimal moves until the end of the game. The important thing for you to remember here now, folks, is it's the optimal moves. If you play the perfect game, or the other player plays the perfect game, is the important thing for you to figure out. There's a lot in this for you to chew. So this is heavy enough going. So we've got a win-loss table here that's partially filled out for us. So what we have here is we have the number of matchsticks on the board. We have the number of matchsticks. So if you imagine, now this game can be a wee bit difficult for you to wrap your head around. Let's say there's a game just to shoot, just let on that they're matchsticks. Doesn't matter what they are. If there's, so who's going first here now? The winning position. So the number of matchsticks remaining 0, 1, 2, 3, and 4. So if the player is going first, if you're going first, if there's no matchsticks on the board, that's a losing position because you've lost. The other person has removed all the matchsticks. If there's 1 matchstick left and it's your turn, how do you win that game? You remove 1. You remove 1. Okay? If there's 2 matchsticks remaining, remember, the player is allowed to lift either 1 or 2 matchsticks. If there's 2 matchsticks remaining, the optimal move is remove 2. So that's a winning position. If there's 3 matchsticks remaining, you can see down here that this is a losing position. Why?
Because a player can only pick up 2 at best, and that'll leave just 1 left for their opponent.
Exactly. If I left 1 matchstick, there's 2 remaining. My opponent, if my opponent makes the optimal move, that will be to remove 2 matchsticks, and they'll win. If I left 2 matchsticks, that leaves the opponent with 1 matchstick left, and they win the game because they collect the 1 remaining matchstick. So, and then we've got 4. 4 is a winning position. 4 is a winning position. Why is 4 a winning position?
If the opponent picks 2, you can pick 2 as well.
So then the opponent would win. So remember, if the player makes all the optimal moves, if I make, what's the optimal move for me to make sure that I win?
Pick 1.
So then the opponent, what do?
Yes, 1 or 2.
They have to pick 1 or 2.
They're in a losing position.
So if they pick 1, they're in a losing position. If they pick 2, they're in a losing position. So 4 is a winning position, because if I make the optimal move will be to remove 1, and that leaves my opponent in a losing position. All right, as we can see from here, that leaves my opponent in a losing position. Okay, so the questions. Why is 3 a losing position? How do you explain this? These are as the questions were written in 2021. Why is 3 a losing position? Are you keeping it a secret? Whatever move you make in this one, you lose. So you'd want to, when you're explaining this in the exam, how would you explain this so that you would maximize your potential to get marks? If you remove 1, your opponent will remove 2, and they will win. If you remove 2, what's the opponent going to do? Remove 1, and you're also going to lose. Okay. So, why is 4 a winning position? How do we explain this? Somebody else now in the room, help me out here. Why is 4 a winning position? What's the optimal move? To take 1. Now there's 3 on the board, and the opponent is playing now. So how do you explain this in the exam? How do you explain that 3 is a losing position? Anybody? Anyone? Anyone? It's my impression of Ferris Bueller there. You're too young to know who Ferris Bueller is. Anyway, we've already discussed why 3 is a losing position. So why is it? Can somebody help me out here to avoid this silence? 3 is a losing position because
Because if you take 1 or 2, still leave the opponent with enough points to win.
okay, so if the opponent can either lift 1 or 2. If the opponent lifts 2, I lift 1, I win. Or no, sorry, we're talking about why is it a losing position. The reason it's a losing position is because if I pick 2, the opponent will pick 1 and they will win. And if I pick 1, the opponent will lift 2. So and they will win. So that makes 3 a losing position no matter what. Okay, so that's the crux of it. Continue the one loss table up to 12 remaining matchsticks. Do you see a pattern? So, here's the task. Pen and paper. Sit. I want you to fill out this the remainder of the way. After about 2 minutes, you'll probably fill out the rest. What I want you to think about now. Remember what we're looking at. We're looking at pattern recognition. As soon as you see a pattern, you should be able to finish this fairly quickly. Don't be shy, folks. You can work together on this if you want. Pen and paper there, folks. You shouldn't need the laptop open at all for this part of the day. No need for it. Has anybody got an idea of what the pattern might be? What do you think?
After every loss, you win twice and then you lose again.
So, what are you saying? You're saying 1-1 loss, 1-1 loss, 1-1 loss, 1-1 loss. Good man. Superb. Superb. Okay. Can you explain why 5 is a winning position?
Because if you, let's say, take 1 and there's 4 left, the opponent can either take 1. If the opponent takes 1, it's a losing position, but if the opponent takes 2, you're in a winning position, you can take 2.
So if 5 is a winning position. 5 is a winning position because if you make the optimal move will be to remove 2, and then the opponent is in a losing position. Simple. So 6 is a losing position. Can somebody else explain to me why 6 is a losing position? 6 on the board. The 6. 1, 2, 3. 6 is a losing position. Think about it. You can explain this. Try and explain it to me in terms of how can you put your opponent into a losing position. And we already know, we've established now that 3 is a losing position. From 6, 6 is a losing position. Why? We can't put our opponent into a losing position. We can only take 1 or 2, and that'll either put the opponent onto 5 or 4, both of which are winning positions. You with me? I can smell some brains starting to fry here. Okay, so we've established the pattern. We've established the pattern now that it's, so 3 is a losing position, 6 is a losing position. What about 9? Losing. What about 12? Okay, so we've established our pattern. There are 21 matches. If your opponent offers the choice of going first or second, which would you choose and why?
Get the opponent to go first.
Why?
Because we've already established a pattern, but after every loss, 2 wins, and 21 is a multiple of 3 because a loss for a multiple of 3. So if the opponent takes 1 or 2, it's a winning position for you anyway. So it would be better for the opponent to go first.
Perfect. So if you and your opponent play the perfect game, you can't win. You can't win from 21, so you let the opponent go first. Because it's divisible by 3, because 21 is divisible by 3, we've noticed here that 3, 6, 9, and 12 are all divisible by 3. So therefore, if we go 15, 18, 21, 21 is a losing position. So we let the opponent go first. So that's pattern recognition. That's pattern recognition. I think there might have been one last year as well. There's another one here. This is the one that came up last year. We'll have a quick look at this. Because this is another good one. It's a different way of doing it. So the reproduction rules of honeybees are quite remarkable. Females lay eggs, and if an egg is fertilized by a male, it will hatch as a female. Unfertilized eggs hatch as males. The illustration below shows the ancestry tree for a male honeybee, shown at the top of the tree. There are 5 generations shown. Draw and label the additional generations. So, this is a pattern recognition question. So this is more graphical. You should be able to see the pattern. You should be able to see the pattern straight away. Maybe not straight away. Whenever I was looking at this, it took me a minute. To figure this one out. So you're given here now generation 1, 2, 3, 4, and 5, and you're being asked to draw generation 6 and 7. Okay. Can we see a pattern? You can. Keep it to yourself for a wee second, because I want a few people to see it before we confirm it. This was last year's question 11. If you've seen it right away, you did better than me now. Because as I was looking at this over the weekend, and I was looking at it going, where's the pattern here? And then whenever you see it, you can't unsee it. Anybody else got it? You've got it. Do you want to explain it to me?
So like the male always, the M will always produce a female and female always produces a male and female.
Very good. So the male always produces a female. And the female always produces a female and a male. Very good. So we can see here now female produces female and male. And we've got male producing a female, male producing a female, and female producing male and female. So we've got our pattern. So what comes here? What comes after this?
Female and male.
Female and male. What comes after this?
Female.
Female. What comes after this?
Female and male.
Female and male. What comes after this?
Female.
Female. And what comes after this? Female and male. So it's easy. It's easy once you recognize the pattern. Until you recognize the pattern, it's rocket science. All right? So that's what you want to be looking for. Look for the pattern. And then, I haven't got the solution up there. But anyway, you get the idea. So you had to draw the label diagram of the additional generations. So that's the crux of it. I'll actually show it to you here. American scheme higher level. There's the whole solution there now from the marking scheme. I've given you the marking scheme for these papers. They're in the shared folder. So you can see there, female produces a female and a male. The male produces a female, as we established. And then the female then in the last generation produces a female and a male, and the male produces a female. Well done. Good work. That was excellent. So you're looking for the pattern, and it's just a matter of finishing the question once you've established the pattern. Okay, the next question now is on decomposition. So what is decomposition? Decomposition is breaking a larger problem down into smaller, more manageable problems. Larger problems are harder to solve. So, for example, if somebody asked you, how does a bike work? Well, it's not so easy to explain how a bike works. But it's easy enough to explain how the pedals work, or how the brakes work, or how the steering works. So this is what decomposition is. We take a large problem that might seem impossible to solve. We break it down into smaller problems, and then we can solve it. It makes it easier to solve it. That's all decomposition is. And this has come up. The matchstick problem came up again. Okay. So the matchstick game. If we remember the matchstick game from 5 minutes ago, we have a new matchstick game. There's 2 new rules. Matches are arranged into 2 separate piles. A player can remove any number of matchsticks from a single pile on their go. So we've got pile X and pile Y. So this is pile X and this is pile Y. The player who removes the last matchstick wins. Okay. So we haven't got a question here. So below is a partially complete decomposition diagram for the game scenario in which it is player A's turn and there is only one matchstick left in pile X and 2 matchsticks left in pile Y, denoted by the 1 and 2. So this is the diagram. So this is our pile of matchsticks. We've got 1 matchstick in one pile and 2 matchsticks in the other pile. So here we have it, if you can see this. 2 matchsticks, 1 matchstick. Okay? The purpose of the diagram is to depict the eventual outcome for every possible move from this point in the game. The left-hand branch of the diagram has been completed, covering all eventualities if player A removes 1 matchstick from pile X, denoted by AX1. So what's going on there? So, if the player removes 1 matchstick from pile 1, or pile X is what they're calling it. 1 matchstick from pile X, isn't that it? Yep, AX1. So we're removing 1 matchstick from pile X, and what are we left with? We're left with 0 and 2, as you can see here. I've just removed that, 0 and 2. So then player B goes and removes 1 matchstick from pile Y and 2 matchsticks from pile Y. All right? So they're the two possibilities. So we're breaking the problem down into smaller parts to demonstrate what happens under these two conditions. So if the player removes 2 matchsticks from pile Y, player B wins. If player B removes 1 matchstick from pile Y, we continue playing, and player A removes 1 matchstick from pile Y, and player A wins. Okay, so the task is to complete this diagram. Okay, so what you've got to do now is on your pen and paper is draw out this diagram. But the question is now, where do we see what the question says? The purpose of the diagram is to depict the eventual outcome for every possible move from this point in the game. The left-hand branch of the diagram has been completed, covering all eventualities if player A removes 1 matchstick from pile X, denoted by AX1. Complete the diagram to illustrate all possible moves and show who wins in each case. So you've got to complete this. So let's have a crack at it. We've shown you how to do the left-hand side. Now we're showing you how, we've already told you what's happening. The first one is remove 1 matchstick from pile Y, and this one here is remove 2 matchsticks from pile Y. All right? Complete the diagram. Have we got a pen and paper, gentlemen? Okay, let's go for it. Has anybody got a possible solution for me? We'll just give it another 30 seconds. Okay, so let's have a look here. So we're removing one matchstick from pile Y. So we're removing one matchstick from pile Y. So what goes in here? 1 goes in there. Then what happens? We have two options now. So B takes 1 from X and B takes 1 from Y. And then what goes in here? What goes into the boxes? 0, 1 and 1, 0. And then A takes 1, there's only 1 left, and then A takes 1, so A1's all them all there. Okay, very good. What about here? Player A takes 2 from Y. So we've got a box here that says what? 1, 0. So what happens next?
B takes 1.
So what's inside the box?
1, 0. So now when they take 1, it's 0, 0. So we win.
So who wins?
B.
B wins, exactly. Well done. So here we have 1, 1. B takes 1, BY takes 1 from Y, and A takes 1 from X, leaving A as the winner. Player A wins. So B takes 1 from X, A takes 1 from Y, so player A is the winner. So player A is the winner in this eventuality no matter what. So then we'll go over here. We've removed 2 from pile Y. So B has no option but to remove the one remaining match, and we are left with B as the winner. Okay, so that's a decomposition exercise. So there's absolutely no chance on the planet that anybody could solve that all in one go. You have to break it up into smaller tasks and do it one at a time. And then it's all solved like that. So that's a decomposition exercise. Likely to come up in the exam. That was 2001, was it? What do you see? 2001 it was. Aye. Abstraction. Abstraction, this is the one that people, this is the area that people struggle with the most. What is abstraction? Where did you use abstraction? Questions come up in the Leaving Cert, come up last year and the year before. Where did you use abstraction to solve this problem? The reason being is abstraction means more than one thing. Abstraction, for example, if we were to talk about abstraction as far as a house is concerned, well, what you can do, what you naturally do in your house, if I says to you, right, there's this building, it's got windows and doors and a roof, and inside it, it's got a living room and a kitchen and all this kind of stuff. You naturally put all that stuff together in your head. That's a house, okay? A car, what's a car? So in your head, if somebody's explaining to you a vehicle with 4 wheels and a steering wheel and seats inside it and runs on petrol or diesel or a battery nowadays, or both, that's a car. So that's abstraction in one way. So basically what you're doing whenever you are using abstraction is you get rid of all the unnecessary detail of, when we're talking about a car, when we're talking about it has 4 wheels, it has seats, it has a steering wheel, it runs on a fuel or electricity. You cast away all that detail because we don't need all that detail for you to understand in your mind that it's a car. Same applies for a house. You discard the unnecessary detail that doesn't help you to solve the problem. So that's one way that we can use abstraction. Another way, which is kind of the same thing, is in the previous question here, we've used to represent piles of matches. We've used a number 1 we've used a number 1 to represent a pile of matches with only one match in it, and we've used a number 2 to represent a pile of matches with 2 matches in it. We've used the letter A to represent a player, and we've used the letter B to represent another player. So we're casting away all the detail about player A and player B. We don't care who they are, what they look like, where they're from, what height they are, what colour of runners they're wearing. Doesn't matter. So that's abstraction. We discard the detail that we're not interested in, so we can use a letter to represent a person or a player, and we can use another letter to represent the other person or player. So abstraction allows us to create a general idea of a problem. This is another layer of abstraction. Here we remove all specific detail that do not help us to solve the problem. This helps us form an idea of the problem called the model. This is like a formula in maths and a fraction or a function in Python. So let's say, for example, let's say you're writing a formula or a function for the area of a circle. So we all know that pi r squared is the area of a circle. So there's abstraction going on there. What we're using is we're using the symbol pi to represent 3.14. We're using the symbol r to represent the radius, pi r squared I. And then if we create a function using that formula, we can figure out the area of every circle. And whenever we figure out the area of every circle, we call that the model. Okay? So, and here's another example of a model. The model of baking a cake. A cake has ingredients. Each ingredient has a specific quantity, and each cake needs to have a specific time to bake. We don't need to know what those ingredients are. We don't need to know what the quantity is, and we don't need to know how long it takes to bake it to generate the model. They're specifics. We put them to one side because we don't need to know them for now. This is the reason why abstraction is so abstract. It's so difficult for people to wrap their heads around, because there's multiple ways that it can be used to solve problems, and so we're going to use it now in the simplest possible way to solve problems. A model represents all cakes. From the model, we learn that what all cakes look like. They look like they have a cooking time, they have ingredients, they have a cooking temperature, they have ingredients, they have a cooking time, and they have things that you need to do. So from here we can learn how to bake any cake. So back to the matchstick problem. Explain the use of abstraction in developing the solution to problems. So method 1, find all possible outcomes to the game. To solve the decomposition diagram, we ignored all other detail and we focused on one. When faced with one matchstick and 2 matchsticks, we play out x1 without considering other moves. So that's one part of abstraction. Remember, when you're dealing with abstraction, you ignore all other detail. You ignore all the other detail that you're not interested in. And in this case, when we're dealing with AX1, where do we go back? AX1, when we're dealing with AX1, where we removed one match from the left-hand side, we focused on the left-hand side here. We focused on what happens when we remove one matchstick from pile X. And we focused on that. And we ignore all of this. So this is abstraction. We ignore all of this and we just solve the left-hand side first. Okay? That's abstraction. Ignore the unnecessary detail that you don't need to solve the problem. Method 2. Where did we use abstraction? Abstraction allows us to use representation for physical actions and objects. So, we use 1 and 2 to represent one match in pile X and 2 matches in pile Y. So this is an abstraction. We don't need to know that they're matches. We don't need to know what they look like or anything else. We can just represent them as a number 1 and a number 2. Simple. A and B represent the players. We don't need to know anything about the players. We just need to know that they're 2 different players. So we represent them as A and B. And we can solve the problem from there. It doesn't matter anything. Any other details about player A and player B are discarded. That's abstraction. You have 8 so here's an abstraction question here now. So this is quite tricky. This one came up last year. You have 8 coins and 2 pans, 2 pan scales. Both the coins and the scales are gold-plated, and the diameter and circumference of all the coins are exactly the same. The coins are worth €2 and €16. 7 of the coins are genuine and weigh the same amount. 1 of the coins is fake and is heavier than the other ones. Explain a way that the fake coins can be found in the minimum number of weighings, and outline your use of abstraction in tackling this problem. So, from what I've explained to you there for the last 10 minutes, I probably confused the line in areas. We'll solve this problem next. We'll solve that problem next. But we'll solve this one first. Outline briefly your use of abstraction in tackling this problem. So, what I would suggest to you do, remember, the common theme in all explanations of abstraction is to discard unnecessary detail. Read the question again. Identify details in the question that are irrelevant. Put a line through them. Okay? Identify something. So, go for it. Read the question there and tell me something that we don't need to solve the problem.
The worth of the coins.
The worth of the coins. The coins are worth €2, totaling €16. Anything else?
The diameter and circumference.
The diameter and the circumference. Okay. We might need that. We might need that. What do we need? We don't need to know the diameter. We don't need to know the circumference, but what we do need is we do need to know that they're all the same. That's all we need. You're right. We don't need to know the diameter. We don't need to know the circumference, but what we do need to know is that they're all the same. There's more. Exactly. Gold-plated. Who cares? Don't need to know that to solve this problem. Don't need to know that they're gold-plated to solve the problem. So that's how abstraction came up last year. Now, let's have a look at the question itself. Explain a way that the fake coins can be found in the minimum number of weighings. So we have 8 coins. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 coins. Now, I've had a look at this. And there's a few different ways that you can that this can be solved. But it's asking, explain a way that the fake coin can be found in the minimum number of weighings. In the marking scheme, there are 3 possibilities. Like if you did it in a certain number of weighings, you get 1 mark. If you did it in less, you get 2 marks. And if you did it in less again, you get 3 marks. So if you have an answer, you'll get marks for it. So whenever you do your exam, remember, answer the question the way that you know how to do it. And then, if you can do it a better way, go back and have a crack at it. But don't waste time on it. Don't waste time on it. You go back to it at the end if you want. Okay? So, explain a way that the fake coins can be found a minimum number of weighings. How many weighings do you think you'd have to do to solve this problem? 2. Explain that.
So you have 8 coins, divide and you split them into 4. And if you put it on the weighing scale, the heavier coin should be one of the other piles, and whichever one's heavier, you take that out and take any 3 coins. You take the pile out, then you have 3 in that pile. Take out 3 coins.
So take 3 out of this one.
Yeah. So they take 3 out and put 2 on one pan and one on the other one. No, sorry, not 3. Sorry. Take the split again, put it in 4.
So split them again and put them 2 and 2, is that it?
Yeah. Then you find whichever's heavier, then you can split them up again. So that's 3 then.
So that's 3.
Yeah.
That's good. That's good. So we've done it in 3. There is a way that we can do it in 2. So basically, what you've done there now is what you did there was you were left with 4, and you split them in 2, and you know the heavier one is going to have the coin that you want. So now you just weigh those two. You weigh those 2, and the heavier one is going to be the fake. Anybody have a different solution? Anybody able to do it in 4? Because you get marks for 4. Don't be shy now, folks. Because you get marks for this. Anybody figure out how you can do it in 2? This is tricky. This is tricky, and it's really, really clever. I'm trying to think if I can remember the solution myself. I have it written down because this is really clever. And don't. Okay. An idea? You have an idea? Okay, let's go for it.
Because in the question there's 2 it says 2 pan scales. So if we split 8 into 4 groups of 2, so 2 on all pan scales, you can find out which one's heavier, judge based on that, and then take that and split them up and see which one's heavier then.
So you're on about a set of scales and another set of scales?
Yeah.
You're being crafty there. That's a play on words. We've only got 2 pans on one scale. So So it can be done. It can be done, and it's quite clever. Well, I put you out of your misery. Put you out of your misery. Right. So what we do is we split our 8 coins into a group of 3, 3, and 2. Okay? So we get our 2 3 piles, and we put them on the scales, and we put the 2 away out of the road. If the heavier coin is in one of these piles, we can discard the other one. If these are the two of the same weight, this is the easier one. If these both are the same weight, we just put these 2, and the heavier one is is our fake coin. If one of these is heavier, we do the exact same thing again. We split this in 3, put that coin there, and that coin there. If these 2 are the same weight, that's the heavier one. If one of them is heavier, then we've identified the heavier coin. 2 weighings. Really clever. Expecting you to come up with that solution in the exam, that's tough. That's tough. Hence the reason why your solution, you'll get 2 out of 3 marks. If you have a solution that uses 4 weighings, you get 1 out of 3 marks. All right? So don't be thinking, and anyway, in the question, they don't tell you how many weighings. They don't tell you how many weighings, so you'll be walking out the door in the exam thinking you did brilliant, and you probably did. Okay? If you got it, and if you got the 3 weighings, really, really good. If you got it in 2, superb. Okay, we're out of time, folks. There are a few in that PowerPoint in your own time. You can go through algorithms, and you can see that there's lots of stuff on there that will walk you through. There's an ordinary level question from a couple of years ago, and this will walk you through the question, the ordinary level question. We have a higher level question here on flow charts. This is quite straightforward here now. This flow chart stuff, but it's all there. All the stuff is in, and some of the solutions are in the notes in the PowerPoint. Algorithms. And is there anything else? And that's it. That's us for the day. Folks, thanks very much for your attention, and I really appreciate it. And just a wee reminder, in your Python exam, you have the Python reference guide with you. Make use of it, because it could save you a fortune of time in the exam when you're under pressure. So whenever you're preparing for the exam, have your Python reference guide on you the whole time. That's the best bit of advice that I can give you. Have it on you and refer to it so that you know what's on it. All right? Hello. So you should have received an email. You know whenever you signed up, when you signed up, you would have submitted an email address. Aye, and then it should be there. What I can do for you, will I show you? Will I just I'll give you a URL for it. Google Drive. Copy link. Okay, so I'll go to the first page of the PowerPoint, and I will put it here. Oh no, I'll go tiny URL. Skip. Scan me. So can you scan that on your phone there now, and that'll get you what we're looking for. Let me know if you can access the PowerPoint. Can you open the PowerPoint?
Yeah.
Superb. Then that's it. You have everything. You have everything.